Hello, Math 120, and this is Professor Gonzalez, and I'd like to do some problems from Homework Assignment 6.5. Now, what we're doing here is we are taking a look at radical expressions, and we would like to rationalize those. Now, rationalizing it means essentially turning these numbers in the denominator, which are irrational numbers, into rational numbers. In one way, you can say it, I guess, in a very basic way, is you got to get rid of the radical. You're trying to eliminate this symbol from the denominator. We don't care if it's in the numerator. We're trying to eliminate from the denominator. Probably comes from ideas that, if you want to add or subtract rational numbers, things like that, you're going to want to, have the denominator as easy as possible. You don't want those radicals down there. That's probably kind of where that came from. But anyhow, first question says the process of rewriting an expression without a radical in the denominator is called rationalizing the denominator. Okay. That's what we're doing this whole time on this, 6.5, right? Okay, so the very first one, it says to rationalize the denominator, multiply the numerator and denominator by what? Well, essentially, what we're doing here, let me just do it right up here. If I had the square root of 5 over the square root of 11, the logic here is, we always need to know what is the root index. And the root index, if you don't see it, is definitely going to be a 2. Now that is going to let us know, right, that we need to have 2 of the same factors to simplify something in the radical. So notice I do have 11. Well, if I can multiply it by the square root of 11, then I'm ultimately going to have 2 of them, which means the power matches the index, and I've just rationalized the denominator. So that you can, if you multiply the denominator by a number like square root of 11 and the numerator by that same number, the fraction is still equivalent to the original fraction. Now we're going to have 5 times 11, which is the square root of 55. They didn't actually ask us to do all this work on this one, but I'm just showing you what it looks like when you rationalize the denominator, and also, more importantly, knowing the strategy, right? Square root, I need to have 2. I already have 1, so I'm going to multiply by another 11, which gives me 2 11s, right? 11 squared, 11 times 11, and that allows me to rationalize the denominator. So they only wanted us to identify what do you need to multiply by, the denominator. Well, that's square root of 11. Now let's actually do this. Rationalize the denominator if possible. Simplify the rational expression by dividing the numerator and denominator by the greatest common factor. Okay, well, here's how I think about it. Once again, it's always important to realize that this is a square root. And if it is a square root, I know I'm going to need 2 2's, 2 factors of 2's. I only have 1. But if I had 2, right? Now we could also show our work, but really what we want to do is we want to get fast at knowing that when you have the square root of the same number, that's just going to be 3, right? It's the square root of 9, but it always simplifies down to, because you have 2 of them, right? You have 3 times 3 is squared, and square roots undo squares. Anyhow, so that's pretty quick. Now remember, I guess I did this in red before. I multiplied the denominator by the square root of 2, so I must also multiply the numerator by the square root of 2. And so I get my answer. 1 times root 2 is just root 2. So there's the final answer right there. Root 2 over 2. Let's do another one. When I try to rationalize the denominator, I usually try to simplify that radical in the denominator first, because life can be easier if I can simplify it and make the numbers smaller and easier to work with. But look at that. 3 times 7 is 21, so there's no perfect square in there. So there isn't any simplification that can happen. So I will then remember that this is a square root. I've got 121. Well, I really need another 21 to make a perfect square. I've got 1x. I need another x. So multiply the denominator and numerator by 21x, and that will rationalize our denominator because now I've got the square root of 21x times the square root of 21x, which just is 21x. And then down below, I've got 7 times the square root of 21x. Now, remember, reducing common factors is always something you do with fractions. And this 21 and x are on the outside. They're not in a radical, so do not try to reduce them with the 21 and x. Those are not like factors. However, I do have a common factor of 7. 7 goes into 7 once, and 7 goes into 21 3 times, right? There was a common 7, and we just simplified it or reduced it out. This gives us a final answer of the square root of 21x over 3x. And that, once again, is simplified. Please do not try to reduce x and x or 21 and 3 because they are not common. This is the square root up top, right? That's the square root, and these are not square roots, so they're not the same. We could only reduce the same exact common factors, and those are not the same. Okay, so this is a good idea to start doing something where it's not a perfect square. We're looking for cubes. That's a cube root right there, because what happens is quickly students get the wrong idea that all you do is just copy this guy and multiply it, and that's kind of what we've done, right? You just take a copy of that and multiply the denominator and numerator. But that's because we wanted a perfect square. So now the game changes a bit. We want a perfect cube. And only perfect cubes will simplify this radical, right? So a perfect cube means I need 3 of the same factors, and how many do I have? Only 1. So I'm going to need 2 more. That is going to give me a total of 3 5s being multiplied, so that's 5 to the third, which would then, in a beautiful way, simplify down to 5, right? Because remember what this is the cube root of 5 cubed. And when the power of 3 matches the index of 3, out comes the 5. And so that's what we have here. Okay, what happens in the numerator? Well, we need to multiply the numerator by the same amount. The cube root of 5 times 5 is 25. And so now 4 times the cube root of 25 is just 4 cube root of 25. This is kind of a thick pen tip when I zoom in. But when I zoom out, I think it's okay. Yeah, it looks kind of nice. It looks like I actually have half decent handwriting when I zoom out. So that's the answer there. That is reduced completely. Please don't try to reduce the 5 and the 25 because that 25 is a cube root, which is not the same as a 5 on the outside without our cube root. Let's move on to number 6, rationalize the denominator. Now, good. It's good again to realize that look at that guy. That index is 4. What does that mean? It means we have to have repeated multiplication of the same factor, 4 of them. And we already have how many? We already have 3. So we already have 3. So I only need 1 more p, right? Now, at this point, what I normally do is just write down p because I know it simplifies out. But you could, I guess you could multiply that and think, wait, fourth root of p cubed times the fourth root of p is p to the fourth. Well, then you're going to get to the same place, right? Because the power and index matching, which gives us a p. And that's how you rationalize, right? So when you see a square root, you'll need 2. When you saw a cube root in the last problem, you needed 3 of a perfect cube. And now we've got a 4. Well, you need to have 4 copies, which is a perfect fourth power. Okay, so you have to really, really pay attention to the root index in order to do these problems. Up top, well, up top we had the same, we must multiply by also the fourth root of p. And then we multiply 14 times the fourth root of p is just 14 fourth root of p. And then there you have our final answer. Excuse me. So we've got 14 fourth root of p. We've rationalized the denominator, assuming, it also did say assume all variables are positive, so we didn't have to worry about issues of using the absolute value. Okay, game change here. Well, how am I going to rationalize that denominator? And so often what students will first guess is they'll say, well, I'm going to use root 5. which that's pretty reasonable because that worked last time. But look at when we distribute it, you get root 5 times root 5, which is 25, which, yes, that rationalized. But you also have to multiply it times 1, which gets you root 5. Dang, we still have a root 5. So that strategy failed miserably. So that did not work at all. Get rid of it. Get out of there. So what we have to do is we have to remember back to some previous learning that said, hey, wait a minute, if I had A plus B times A minus B, some nice things happen, right? Wasn't that a difference of two squares? Didn't it just become A squared minus B squared? And yeah, what happened, let me just kind of verbalize what happened. Well, all the nasty stuff in the middle zeroed out, and you have perfect squares. A is a perfect square and a B is a perfect square. Well, guess what perfect squares do? This is another problem. Guess what a perfect square does to the square root of 3? Well, a perfect square, so the square root of 3 times the square root of 3 is just 3, right? So this is a really powerful thing when we're trying to rationalize the denominator. So I'm going to go ahead. I probably should have put that over a little bit because I need, oh yeah, I've got my little tool here. I can just go like this. Oh, darn it, I didn't get it all. Yep, it all moved anyways, good. So we'll just move that out of the way. How do we get it back? Okay, move it out of the way. And here we go. So using that logic, I want to kind of create this idea like the difference of two squares. Now in rationalizing the denominator, it actually has a different name. It's called the conjugate. So the square root of 5 plus 1, the conjugate is square root of 5 minus 1. But you'll see that the philosophy and how we multiply is going to be the same as the difference of two squares. Must multiply the numerator by the same thing. On this first trial, I think I'm just going to show you all the work. Well, let me show you how fast it goes first of all. If you believe that this is a difference of two squares, well, then you're going to believe that it's the first term is squared, the middle stuff all goes away, and then the last term, 1, is squared. And so if you believe that formula, which you really need to because it's going to go so much faster, the square root of 5 squared is 5. 1 squared is 1. 5 minus 1 is 4. And the denominator is rationalized, right? Now, if you didn't believe me with this stuff, it looked like I just made up a bunch of crap. Well, what you do is when you don't believe the instructor, you take that stuff right there, right? And you do it on your own. Let's do it on our own over here. Because who knows if Gonzalez is on top of this or he's just making stuff up. So we have square root of 5 plus 1 times the square root of 5 minus 1. Let's go ahead and just multiply it out. Root 5 times root 5 is the square root of 25. You're going to make me go through this pain. Do you see what time it is? It's 2:11 a.m. and I'm going through all this extra work. Root 5 times a negative 1 is minus the square root of 25. Now we've got 1 times square root of 25, or square root of 5 is square root of, oh my gosh. I'm getting too sleepy right now. Let me try again. So you got to do it right for it to work out though. Let me go back to that. Okay, let me start way back. Let's just start it all over again. Yeah, I'd like to say that I get paid by the hour here, but I don't. So anyways, I should not do so many mistakes. Square root of 5 times square root of 5 is the square root of 25. Square root of 5 times a negative 1 is minus the square root of 5. Positive 1 times the square root of 5 is plus the square root of 5. 1 times negative 1 is negative 1. Look at what beautiful things took place. The middle terms are opposite. Negative square root of 5, positive square root of 5, 0. This square root happened to be a perfect square, so it's now rationalized. And also this is a perfect square. And 5 minus 1 is 4. Hey, I wasn't so crazy. Look at, I got the same thing. But I didn't have to go through all this work because I knew that this was a difference of two squares, and every single time the middle terms are going to zero out, and the first term is a squared, perfect squared, and the last term is perfect squared. Okay, now let's I think I'm going to have to move this over now a little bit again, just to kind of get that out of the way, because I think I'm going to have to do a little bit of simplifying or something, because remember, we're not done with this problem. Distribute. So now this is 20 square root of 5. 20 times the negative 1 is minus 20. We did everything right, but did we simplify if possible? No, we did not simplify. And guess what? This will simplify. Okay, so the really proper way to simplify is to factor the numerator and factor the denominator. Now I could factor out a 20, but I'm not gonna. I'm just gonna factor out a 4 because I can see there's a 4 down below that wants to be reduced. So I'm factoring out a 4 out of the numerator. When I factor a 4 out, I'm left with 5 root 5 minus 5. And you can see that. You can verify that because if you distribute 4 times 5 root 5, you get 20 root 5. And distribute 4 times the negative 5, and you get negative 20. So that was all good. So I know I factored correctly. And let's go ahead and reduce common factors of 4. And I'm left with my final beautiful answer, which is, I'll put a little arrow here, that's just going to be 5 root 5 minus 5. And there we go. 5 root 5 minus 5. Okay, let's zoom out because my handwriting looks better like that. Now let's go over here to number 8. And number 8, we got the same thing going on again. Got the same thing going again. We've got to rationalize the denominator, and we've got something kind of nasty here. And so what we want to do is we want to multiply by the conjugate, which is the same root 8 instead of minus plus, and the same root 6. That is going to ensure us that we get this difference of two squares business. That's going to ensure us that the denominator is going to be rationalized. Well, we just went through it. When we multiply that, we know it's going to be the square root of 8 squared minus the square root of 6 squared, and all the middle stuff goes away. Square root of 8 squared is 8. Square root of 6 squared is 6. 8 minus 6 is 2. We got a 2 down there. That was beautiful. Now up top, maybe not quite as nice. Up top is going to be the square root of 6 times. Now remember, they're not like radicals, but they do have the same indices of 2, and you're allowed to multiply them because they have the same index. So root 6 times root 8 is the square root of 48. Distribute again, plus root 6 times root 6 is square root of 36, but let's just call, that's just a 6, right? Square root of 36 is just 6. Now, we do need to kind of identify the square root of 48. Is there a perfect square factor in there? And how about the square root of 9 times this? Nope. Wait, what is it? The square root of 48, what's in there? I believe there's a 16 in there now, if I think about it a little more. 16 times 3 is 48. So yes, there definitely is a perfect square because 16 is a perfect square, right? Square root of 16 is 4. So I can rewrite that square root of 48 as 4 square root of 3 plus 6 all over 2. Now once again, we want to factor out if we can reduce that 2. And I see a common factor of 2 with a 4 and a 6. So I factor out a 2, and I'm left with 2 root 3 plus 3. And I've got a common factor of 2 that can be reduced, leaving me with my beautiful answer of 2 root 3 plus 3. That would be 2 root 3 plus 3. Now moving on down over here. Oh, it's getting tougher and tougher. Now the denominator is not tough, it's just the numerator is going to make the problem a little bit tougher. But we could do it. Can't we? Yes, we can. So now we go ahead and multiply. The denominator is driving this whole train here, right? Because we want to multiply by the square root of 5 plus the square root of 3, making sure that these signs are opposite so we get this conjugate, also giving us this difference of two squares situation. Of course, multiply the numerator by that same exact quantity, and beautiful things happen down below because we got the square root of 5 squared minus the square root of 3 squared, which gives us 5 minus 3, which, gosh, they're not very creative with these questions. 2. Down below, again, 2. Up top, well, up top's not going to be so awesome because look what we have to do. We got to go root 5 times root 5, which is square root of 25, which is just a 5. We've got to go root 5 times root 3, which is just square root of 15. I guess just so you can see my colors here. Now I've got to go 9 times root 5, which is just 9 root 5. And I've got to go 9 times root 3, which is just 9 root 3. And this is what, number 9? So now we want to see, are there any like terms that we can combine, like radicals? Well, that is a constant value, not just a constant value, but let's say it's a rational number, right? Now we've got these radicals. We've got the square root of 15, and it doesn't simplify down because it's just 3 times 5, no perfect square. We've got square root of 15, we got square root of 5, we got square root of 3. They're all different radicals. We cannot add those together. And so that is the final answer. Rationalize the denominator. So we start getting the false idea because we say, well, if that's a square, oops, that just jumped. It says if that's a square root, which it is, root index of 2, that's a square root. Well, then I just multiply the denominator and numerator by 8 squared root of 5. That will work, but you don't really need that 8 because all you really need, whoops, I don't want that. All you really need to rationalize the denominator is to turn the radical, right, into a rational number. The 8's already good to go, right? 8's already out of the radical. So the minimum, all we need, it says we need 2. Well, we have 1 square root of 5 inside, so we need another square root of 5. So that's the minimum. We always like to do the minimum because if we don't do the minimum, we're going to have to then do a bunch of reducing in the end. Okay? Now don't forget, do not forget, what color am I going to make this? Do not forget that guy, right? That guy is right there, so don't forget your negative sign. Now down below, some beautiful things are going to happen. We have the 8, don't forget your 8, but we do know that square root of 5 times the square root of 5 is square root of 25, right? This stuff you should start doing in your head is just 5. So, but it does get multiplied, so don't add it. It is being multiplied, okay? If I were to show my work, I guess, a little better in some ways, a lot of times we get to 120, you don't show quite as much work because it starts becoming, I don't know, you start doing some of the stuff in your head, but that would be 8 root 5 times root 5. Well, you know what? All of these, that's being multiplied, but so is that. They're all being multiplied, right? So then let's just multiply those two. We can multiply in any order that we want. We know square root of 5 times square root of 5 is square root of 25, which is just 5. And now we know 8 times 5 is 40, right? So we've got that taken care of. Where am I at? Where am I at here? Number 10. Just making sure I'm not missing something. Yeah, okay. So 8 times 5 is 40. Now, the disadvantage of multiplying this is at this step, which is no problem if you do, but you're going to notice 15 has a 5 in it also. So you're going to have to sort that out in the end. So sometimes leaving things factored is just quicker. Look at what happens up top. 15 times root 5 is going to give you 15 root 5. And because we didn't factor it, it made it a little easier maybe to see that 5 goes into 5 once and 5 goes into 15 3 times. And once again, don't forget the negative out in front. We're going to get an answer of negative up top 3 root 5. Remember the goal, no radicals in the denominator, and we did that. It's just an 8. So the answer is negative 3 root 5 over 8. Let's keep it going. Okay. Now, once again, you're going to see this, and you say, okay, he said it's square root. We're looking for 2. It's always good to know what that root index is, and it is true. You could, in fact, multiply the denominator by the square root of 45 and that will work. And that will work. You're going to have a lot of reducing, simplifying and reducing to do. But this problem, you're not going to get too punished if you do it that way. And I would never take off points if you did it that way. But personally, I like to simplify this guy down as much as I can, if I can. And I see that the square root of 45 is the square root of 9 times the square root of 5, isn't it? And the square root of 9 is just 3. So the square root of 45 can be simplified down to, instead of square root of 45, 3 root 5. Now, the reason why I like that is because what do I need to do to rationalize to get rid of the root 5? Well, I have one of them. I need 2. So let's multiply it by just root 5 over root 5. And so you see, I don't have to do as much simplifying in the end. I can see here that this root 5 times root 5 is square root of 25, which is just 5. Don't forget that you also have this 3 that's being multiplied, so the denominator is 15. And up top, we've got 5 root 5. Oh, I better reduce, right? So 5 goes into 5 once, 5 goes into 15 3 times, and we are done. Had you multiplied by the square root of 45, you would have to simplify that in the end and then reduce. You get the same answer. So it's not a big penalty, it's just a little bit more work. Our final answer is going to be the square root of 5 over 3. Square root of 5 over 3. And then let's take a look at the next. Rationalize the denominator. Okay, great. This is a good one. Because once again, you got to be really cognizant that that is an index of 3. What does that mean? It means in order for us to rationalize the denominator, in order to get that 5 out of a cube root, you need 3 of those 5s. And how many do you have? You only have 1. So we must multiply this by the cube root of 5 times 5. So now I've got 1, 2, 3. And in the end, that denominator will be just 5, right? Because when you multiply all those up, that gives you the cube root of 5 cubed. And whenever the power matches the index, out comes the 5, and that's what we did. Okay, and actually these numbers look very similar to an earlier one, but slightly different, I guess. Wish they had more variety. Once again, I say that every once in a while, maybe every time. So the denominator is the cube root of 5 times 5. The numerator is the same thing. I'll just write it 25. 7 times the cube root of 25 is just 7 cube root of 25. That will not reduce, is a fraction. And that is the final answer, 7 cube root of 25 over 5. Okay, let's see here. Number 13. Rationalize the denominator. Assume that all variables are positive. Yes. Basically letting us know, well, it's cube root, so it doesn't matter. But letting us know with these problems, whenever they've got a variable in there, assume all variables are positive. There's no variables. Ding dongs. Anyways, so that's doesn't even matter there. But whenever they have many times in this book, whenever they have a variable in the problem, which you might have to simplify the radical with a variable, they say assume that, so we don't have to worry about our absolute values with these simplifications. So let's take a look here. Now remember, don't forget, you got to know how many of those. And yeah, you can multiply this by the cube root of 12 times 12, so you have 3 12s, and y times y times y, so you have 3 y's, right? You already have 1, so y times y rather. But what I like to do is I like to take a moment and write that 12 as what? 3 times 2 times 2, and then we have a y. Why do I do that? Because it makes it easy to see the minimum. What's the minimum that I must multiply by? Well, once again, you have to know the game is cube roots, so you need to have 3 of the same. I've got 1 3, I need 2 more. I've got 1 2 2, so I need 1 more 2. I've got 1 y, I need 2 more to make a total of 3, which makes those all perfect cubes. So now up top, just do that again, but let's multiply 3 times 3 is 9, times 2, I should have multiplied that together. Y times y is y squared. So we have 18 essentially up there. I'll fix that the next line. So now, here's the beautiful thing. Well, these are all perfect cubes. So 3 is a perfect cube, so out comes 3. 2 is a perfect cube, so out comes 2. Y is a perfect cube, so out comes y. They're all being multiplied. Up top, we have 2 times this, so we have 2 already outside. The cube root of what is 9 times 2, 18, y squared. Now I know 18 is not going to simplify because you need to have a perfect cube, and we had a perfect square, but that's not enough. That's 3 times 3. We need 3 times 3 times 3. 27, right, to simplify out. Okay, final answer. That's a strike. There we go. Final answer. Up top. Oh, well, before we multiply, I see a common 2, right? Let's reduce our common 2's. Now, final answer. Up top, cube root of 18y squared over 3y. And that is the final answer for number 13. Cube root of 18y squared over 3y. All right. Let's zoom out for a second just to kind of get a bird's eye view of what's going on here. There's our paper. Okay, that looks good. That looks good. Number 14, 15, 16. Oh, almost there, almost done. Rationalize the denominator. Assume that all variables are positive. Okay, let's zoom in and do some work here. Once again, really realizing that that index is 5. The name of the game then is we need 5 of the same repeated factor being multiplied to simplify out of the radical. Well, I have 4 of them, right? X to the 4th. So I need 1 more x. I only have 1 y, so I need 4 more of those. And when they multiply it, we are going to have x to the 5th, y to the 5th. And so that is awesome because that will rationalize the denominator. Out comes the x, out comes the y. Up top, you better multiply it by the same quantity, and the same indices, which happen to be, what, 5? 5th root of x, y to the 4th. Now, when we multiply the numerator times 2, we get 2, 5th root of x, y to the 4th. And those x's and y's are on the outside of the denominator, and they're inside of their 5th roots on the inside, so they're not like radicals. So there is nothing more to do, no more simplification. And this was number 14, and we're done. 2 root 5 x, 2 the 5th root of x, y to the 4th, all over xy. And we're done. Number 15, rationalize the denominator. Well, we know now that we better write down its conjugate and multiply it by that. That's going to be root 5, not minus, this case, plus root 3. Up top, better be the same, root 5 plus root 3. Now let's go ahead and do our procedure. Oh, that was weird. Huh. How to change that? Anyways, so now we know down below, all this nice stuff is going to happen down below. We multiply this because they're a difference of 2 squares. We're just going to get a perfect squared minus the other perfect square. And square root of 5 squared is 5. Square root of 3 squared is 3. 5 minus 3 is 2. Every single time it's 2. What are they doing here? It's not, just to let you know, it's not always 2. Now up top here, we're going to have to distribute. 4 times root 5 is just 4 root 5. 4 times root 3 is just 4 root 3. Yes, there is something we can reduce. Now, I do want to say something. Some books will break this down this way, and you might prefer this. Some books would say, well, this is just 4 root 5 over 2 plus 4 root 3 over 2. And this does work, by the way. This is legal. So then you reduce these guys. Reduce that one. You get 2 root 5 plus 2 root 3. And that is legal. I mean, the only thing is what happens that is not legal is when someone comes along and says, I am just going to reduce those 2 guys. Now that's incorrect because of the addition. You cannot cancel terms. They would have to be factors. And the reason why it works over here is because you broke it down where these are factors, so you're legal. Probably the more, just the way that we like to do it so we don't mess up by canceling terms. And the way that it works with polynomials that get kind of big and bad, right, is how do we do them then? Well, the way we did them then was we factored the numerator. And I see a common 2, so I'm going to factor that out, which gives me 2 root 5 plus 2 root 3 over that 2. And now you got a common factor of 2 that reduces. Once again, it's a factor because of the multiplication. And we've cleanly simplified this down to 2 root 5 plus 2 root 3. 2 root 5 plus 2 root 3. And that is the final answer for that problem. And now we're down to our last problem. Save the best for last, right? That's what we always say. I think I can maybe zoom out a little bit. And we must rationalize that nasty denominator. We are going to have to multiply this by its conjugate. We know that's just going to be 4 root 3. Since this is a plus, we're going to use a minus 9 square root of 2. We better do the numerator with the same thing, same quantity, ensuring that our fraction will be equal. What happened down here? Well, like it always does with that kind of when you're multiplying by the conjugate, you get the difference of two squares. You get 4 root 3 squared minus 9 root 2 squared. Well, when you square this first, it's going to be 4 squared. So I guess just to make sure you're seeing this technically, you can use a property of exponents, which would just say this is 4 squared times square root of 3 squared, which could kind of be done in your head, right? Couldn't you say, well, 4 squared is 16, and cube root or square root of 3 squared is just 3. That's what you're going to get, right? And 16 times 3, might as well finish it off, is 48. Same thing with this one. You could say, well, everything inside the parentheses is being squared, so 9 squared is 81. And when you take the square root of 2 squared, that's square root of 4, which is just 2. And 81 times 2 is 162. And 48 minus 162 gives us a negative, whoops, stop moving like that. That gives us a negative 114. Well, that's the denominator, negative 114. Well, we got a lot to do up top, though. Oh, boy. Okay, we're going to have to multiply. Now, you could put a 1 in front just to realize it's 1 times 4 is 4. And root 3 times root 3 is square root of 9, which is just going to be 3. And we can go ahead and distribute. Think that number in front, 1 times 9 is, 1 times negative 9 is negative 9. And root 3 times root 2 gives me square root of 6. I'm going to use blue just to show the distribution of the next term. So let's start with the numbers. A negative 2 times 4 is negative 8. And root 2 times root 3 is square root of 6. And finishing off here, we've got a negative, let's go from here to the last term. A negative 2 times negative 9 is positive 18. And root 2 times root 2 is root 4, which is just, square root of 4 is just 2. Now, I think some things should happen here, like, let's see, like 4 times 3 is 12. And 18 times 2 is 36. And even this stuff in the middle, these are like terms. And negative 9 root 6 minus 8 root 6 is negative 17 root 6. Let's kind of see what we have here. Down below we have negative 114. Up top, well, couldn't I go ahead and add some like terms there? And the answer is yeah, sure you could. We got 12 plus 36, which is 48, minus 17 root 6. Now, leaving the answer like that is really okay. Usually, when you have a single negative in the denominator, or if you had a negative out here in the front, usually we just like to just stick that. Now, if the negative's in the front there, you got to be very careful because you'd have to factor out of the 2. But when it's just an isolated single term, it's easy enough just to pull that negative out front. And that's typically what a lot of books will do, just to kind of make it clean it up in some ways. But either way is technically correct. Okay, I put this one in right here, and that worked just fine. I did not actually go back and redo another problem and put it in this form, but I'm pretty sure MyLab will let you go there because it is equivalent. Okay, that was number 16, which was the last problem of this problem set. This takes care of our homework from section HW 6.5, and I hope that helped out. Take care and have a great one, and we'll talk to you soon. Bye.